Thank you very much, for the introduction. Thank everybody to be here. I'm very happy to give a talk in this nice workshop and the nice period. I've been here already for a few weeks. I'm planning to stay here for a couple of months. For those who just arrived here, we're really trying to work things out a little bit in this working group. I'm going to mention a few things we've been discussing a little bit also in the last few weeks, and I'm going to talk a little bit about the open problems. Not too much because of the spoiler I'm making here, so it's more like a series of 2 talks. Natalia Monina was going to give a talk just after lunch. So my goal here is to prepare the stage for her. And because of this, I decided to essentially not go too much into the actual topic that she's going to talk about or the ideas of the proof and so on. But I'm going to focus on something which is the relation with the Pauli exclusion principle, which typically I don't have the time to talk about. And because we have this 2-type structured talk, I think it's nice to discuss it with this audience. I'm not sure. I heard that I can use the whole Blackboard thing. That was not the case for the working group. If it's not the case online, please let me know. OK, so let me just start a little bit with the setting. Emily told me that I should not use the red. I promise I'm not going to use the red too much. All right, so I just want to start with the setting. Here I'm going to use the white. But I like to use a few colors. So more or less the setting I have in mind is closer related to the first talk we heard this morning. So we work in, let's say, multi-marginal setting. So I want to discuss a little bit the setting where I have n particles, so I have n Hilbert spaces. Just to fix the notation, so H1, Hn are finite-dimensional Hilbert spaces. It was really nice to have your talk this morning because you really kind of prepared the way for this talk. So I just want to fix some notation. So H for me will be the tensor product of these n spaces. They're all finite dimensional. So with dimension, I will typically call di the dimension of hi and d the dimension of h. And what else I want to fix? So if I want to talk about, so the talk is about non-commutative optimal transportation problem with, in particular, attention to what is called the entropic regularization setting, which means essentially to look at the type of problem we've seen in the first talk this morning when I want to minimize, given a sort of Hamiltonian, I want to minimize a transportation problem with given marginal, but we're going to add a little bit of entropy. We're going to add a little bit of positive temperature to the problem. So the object of interest that I have in mind are H. Big H is going to be an Hamiltonian, so a bounded operator self-adjoint over H, so over the big space. So a given Hamiltonian, which for those coming from optimal transport, they kind of replace the cost operator in optimal transport. And I also want to fix notation here. I will denote by S of H the set of states, which means the replacement for the probability measure in this setting means essentially bounded operator, so gamma bounded and self-adjoint over H, but we trace 1. OK? So these.
No positive symmetry?
Yeah, absolutely. Sorry. Here. Thank you. Thank you very much. So non-negative bounded self-adjoint operator with trace 1, which exactly replaces probability measure in the classical setting. And you have mentioned already partial trace. I'm going to just use a notation, which is probably something that people will not like here, or some will like, some will not like. I'm going to, because I only care about one body partial trace, I'm going to denote by trace I, the trace when I trace everything out but the ith component. Okay, so we're going to write trace I here from bounded operator into bounded operator on the single Hilbert space is going to be just the ith partial trace, which is actually meaning I'm going to trace out all the Hilbert spaces but the ith one. Yeah, just for simplification of notation. We've seen the definition in terms of block matrices in the first talk. If you want to see more from a, how do you say, dual perspective, people coming from optimal transport, we are used to see marginal constraints in terms of what happens if I integrate against a function which does not depend on the other variable. You can also define it this way. So I'm going to define the partial trace by something that if I take the identity and I tensor with something that depends on some operator only in the ith variable. So this is in the ith variable. Then I get exactly the trace over the smaller space of the partial trace against u. Yeah, so for all u bounded over hi. Yeah, this reminds a little bit what the definition of marginal in classical probability sense is. Exactly the same as the definition that we've seen this morning, with a little bit of work. OK, this was more or less about notation. What is the problem I'm interested in right now is the following thing. So is entropic QT that also Natalia is going to talk about. So what I want to do, I want to give you a set of marginals, let's say, given states that represent, let's say, your physical system, the one-body operator somehow of your physical system. Typically, we're going to see about this when we talk about fermions, that typically the marginal physically are chosen to be the same because the particles are indistinguishable. But given the marginals, in this case, we study the following problem. So we want to study the inf over the trace of the Hamiltonian times gamma. This is what we saw this morning, right? So we minimize this cost. Now I want to add a little bit of noise. So I'm going to just add epsilon, the trace of a function phi of my gamma. And then I'm going to constrain gamma to have the right partial traces. Yeah, so I'm going to write this symbol for simplicity. OK, so for me, now this means that the trace, the partial trace of gamma is exactly gamma I, and gamma is just a symbol to mean the vector of all the marginals. OK?
Now, any assumptions on phi?
I'm gonna discuss this exactly. So I didn't say anything about this, also the meaning or what phi is. So without this part here, we got exactly the setting of the first talk this morning. So now, what is phi? Well, phi is a function here that goes from, let's say, r plus to r. I'm going to make, of course, some example. We assume typically the following thing. So assume to be convex, superlinear. OK, and let me see actually if I want to sum it, and bounded from below. OK, I'm going to make a few comments about this. Without actually focusing too much on the general level, let me just write you the typical choice that we do here. So typical. The classical example is to use this so-called von Neumann entropy addition. In this case, you just look at x log x minus 1. Okay? So if you choose this type of regularization, okay, this type of function phi, what we're simply doing here, we're trying to understand what is the optimal, with respect to the choice of the Hamiltonian under consideration, the optimal distribution of my particles under the constraint that my particles are in certain given composite state at the level of the single particle operator, and this epsilon simply plays the role of the temperature. Okay, so I'm adding a little bit of entropy to my problem, and I'm going to study this regularized version of the problem that we've seen this morning. Yeah, so for example, in this case, the trace of phi of gamma is simply what is called the von Neumann entropy. And I think that we have many people here that have been here during this workshop, but not all of us. So just to be precise, for those who come from slightly different setup or the one that comes from optimal transport, so I'm really omitting a little bit of details about what I mean with this. Okay, I have a function, I have a continuous function, and I'm writing phi of gamma. Okay, for those that don't know exactly what is the meaning of this, so if I take a continuous function and apply it to an operator, what I really mean, I'm doing spectral calculus, meaning I'm taking my operator gamma, I am diagonalize it, so I'm finding eigenspaces and eigenvalues, and then I'm defining a new operator which has the same eigenstates, but as eigenvalue, the function applied to the eigenvalue. Okay, so if gamma is the sum of lambda I, let's say psi I, then phi of gamma. So if my psi I in this formulation here is the eigenvector and lambda I is the eigenvalue, then phi of gamma is going to be exactly the sum of phi of lambda I. So I'm going to have a new eigenvalue and then the same eigenvector. Okay? Which in practice, by the way, if I want to define just a trace of phi of gamma, I don't even need this, because if I want to trace, right? So if I want to trace my newly obtained operator. In this case, I just get the sum of the function applied to the eigenvalue. So if I don't really care too much about the operator itself, I can simply focus on this quantity by taking, in this case, what I want to do, I'm taking the eigenvalue of my matrix, and I'm going to do really the classical Shannon entropy, free Shannon entropy function applied to this discrete probability measure. Okay? Okay. So let me say, of course, if you have any questions about any of these parts, so as I said, I think some of the people here have seen this way more than probably wanted already in the last 2 weeks. But if you have any question about this, simply interrupt me. So what I want to do in this talk, so as I said, Natalia will have a little bit more time to talk about this problem. I'm going to now write a little bit about what is the type of questions we're interested in and what type of results we have. But then I want to move to a situation where instead of looking at the problem in the way it's formulated here, I want to enforce additional symmetry assumption on the problem. Yeah? So if you think about the typical physical systems, fermionic or bosonic, this is really not the setting they're working with. And the reason is that at this level, in these marginal constraints, or at the level of this problem, I'm working on the full product space. But as we've seen in practice, what we want to do, we want to focus on a subspace, which is the one where, for example, in the fermionic setting, when we have some sort of additional symmetry on the problem. And so I want to discuss a little bit how the symmetry comes into play in this game. Before doing this, let me maybe just mention what is the main theorem that I'm not going to discuss too much in details, but I will use it as a bridge, and then Natalia will discuss more about it later. So let me just write it here in some form, and I will use it as a bridge to go to the symmetric case. So I'm going to just make my life simpler to avoid technicalities and assume that the marginal has no kernel. We have seen actually this already at some point, I think today maybe, in the first talk about the fact that the presence of the kernel of the marginal typically may cause certain dual potential not to exist. It's exactly the reason why this assumption is there. In practice, in the finite dimensional setting, it's really not a problem to avoid this assumption. The only thing you need to work is you work on the orthogonal of the kernel. Everything works just fine. I'm going to write one line about this, but let's say for now, by simplicity, I'm going to assume this. And also in another color, because it's not necessary, but it makes my life easier now, and then maybe Natalia will say something about it. I am going to assume that phi is strictly convex. The main reason why phi strictly convex is important for those who know already a little bit about the story is that strict convexity implies that the Legendre transform is differentiable. And that is kind of an important feature when I want to study the duality of this problem.
It makes it unique, the problem.
Yes, absolutely. That's also a good point, yes. About the minimizer here, this function becomes strictly convex, which also provides a little bit uniqueness for the primary problem as well. OK, so what I want to say with this, well, I'm going to just write the main thing. So I wanted to, we mentioned duality already a couple of times. I want to write it down explicitly. How is the dual problem in this case? Well, I'm taking my primary problem. And duality means I want to write this minimization problem in terms of a supremum over a dual variable. In this case, because everything is finite dimensional, the dual variable is simply bounded operator. So I'm going to write it as a supremum. And the main difference is because this function has this nice superlinear growth to infinity, the main difference is going to be that the dual problem with this epsilon regularized setting is going to be an unconstrained maximization problem. And if you have seen, for example, the dual problem for epsilon equal to 0, the dual problem is again constrained. And the reason is I'm minimizing a linear functional with a linear constraint. So when you do duality in that case, you end up with another constraint. But because I'm minimizing a strictly convex function, actually superlinear convex function here with a linear constraints, I'm going to get a linear part coming from these constraints, but I'm not going to have an extra constraint in the dual. OK, so let me actually write it here in a bit bigger way. So we get that this is the same as the sup over bounded operator. So U1, UN are bounded operator. Maybe I should write UI is a bounded operator over HI. And then there is one part that comes from the linear constraint, which is going to be this. So the sum of the trace of ui gamma I. So this comes by duality from the linear constraints. And then I'm going to have an extra, this time strictly concave contribution in the dual that comes from the convex term that I have there. So I'm going to have epsilon, the trace. And here, essentially, if I want to write the entropic case with the Shannon entropy, I should write exponential, right? We've seen also at the level of the Gibbs state. Because I have a general phi, here we're going to have the Legendre transform of the sum of the potential minus the Hamiltonian divided by epsilon. Okay, so where phi star is the Legendre transform. Yeah, so it's a sup over x of px minus phi of x. So for example, in the case of the logarithmic case, so if phi was in the case of the von Neumann entropy, for example. Now here you cannot see actually. Let me write it here. So for the von Neumann entropy, so phi star of p is simply the exponential of p. Okay?
But you have to have some constraint, right? Of positive semi-definite. That's a
Say again, sorry?
You have a constraint that some matrix is positive semi-definite.
In this case, we don't. No. The potentials are...
In my lecture, when you take epsilon 0, you have a constraint that something is positive semi-definite.
That's a very good point. That's exactly the point. The point is that the epsilon regularized setup doesn't have any constraint on the dual. When epsilon goes to 0, the problem will have a constraint. And the reason why this actually happens is that in the epsilon equals 0 case, you are minimizing a linear functional over a linear constraint. If you think about what happens when I take Legendre transform of something, if I take the Legendre transform of a linear function, I'm going to get something very singular. Because the Legendre transform is essentially the supremum of this difference. If this functional is linear, okay, then I get something which imposes some plus infinity from which I deduce the constraints. In this case, I get completely free maximization problem. Okay? Of course, when epsilon goes to 0, I will end up with some constraints. Yeah? For example, in this case, you see it's going to be a trace of exponential. If I want this to be finite in some sense, I really need to have constraints in the limit. But I don't have the constraints when epsilon is not 0. Yeah. OK, so the first statement was we talked about this duality. So there is this equivalent way to formulate the problem. And the main reason why we care about duality is not only because there is another perspective, but because it gives us an insight on how the maximizers and the minimizers of this problem are. Okay, we have seen a little bit about the fact that Gibbs states appear in a natural way. Let me write it here because I think it's closer to that one, so it's easier. I'm just going to write here another couple of points about this. So what we know is the following. So moreover, so the first thing I want to say is this. So the dual problem, let me call this functional here. I'm going to call it D, and then I'm going to use the notation epsilon gamma. Okay, so D admits maximizers. Not going to discuss the details. Maximizers are not unique because you can always shift them by a constant. That's the only thing that actually can happen. So you have uniqueness up to shifting. At bit maximizers, I'm going to call U1 epsilon and UN epsilon. I'm going to write here unique up to trivial shifting. You can always add constants that sum up to 0 because this term here and also this term here is completely insensitive to that shifting. Okay? This also happens in classical optimal transport. That's one thing. And the second thing I want to say is that there exists also a unique minimizer gamma epsilon with the right marginals. And this minimizer has a specific relation to the dual problem, which is I can write gamma epsilon in the form of a Gibbs state. We saw today that Gibbs state means I'm taking exponential of minus the Hamiltonian divided by epsilon. That exponential is there because the entropy typically used is the Shannon entropy. In this case, I'm not going to get exponential, but I'm simply going to get the Legendre transform appearing in the formula. Yeah. So what I'm going to get here is going to be that gamma epsilon is phi star. I'm going to write it now derivative of phi star, and then I get the sum of ui epsilon minus h divided by epsilon. Okay, so you get a formula that relates the two. Yes?
Yeah, Lorenzo. So in the original problem, it's an optimization problem of like the global density matrix, or whatever you want to call it. And then if you go to the dual one, it becomes a local thing. So
It becomes a? It becomes a what?
a local thing. So you're optimizing over local UI.
You mean using UI? So I'm using, in the dual, I'm using a structure which is splitting.
UI.
Right.
Whereas in the original problem, it's like the full thing.
That's true.
So this should already have a flavor of that original problem.
I think the flavor is in the constraint, right? I think the flavor is already in the constraints. I get your point. The constraint is already something that somehow is splitting the problem in some sense. So that's the reason why eventually the maximizer will have automatically the structure of sum, which is what I think you're saying, right, in the dual problem. So I think it's related to the type of constraints that you have here. Yeah? Yeah. Thank you. And in the case of the von Neumann entropy, we get exactly the type of Gibbs state we've seen already in the first two talks. So in the von Neumann entropy, we get the gamma epsilon is really an exponential. It's an exponential of a sum minus h divided by epsilon. So in the case of the Shannon entropy, you get exactly the following thing. You get that if I constrain my problem to have given marginal, which may not be the natural one that my physical system want to be in, then my ground states, my condition ground states, will essentially be a Gibbs state, but with respect to a new Hamiltonian, which is not h anymore, but it's going to be h minus the optimal potential. Yeah? So in some sense, if I fix a different type of marginal, which is not the one that my physical system want to be, I need to correct my Hamiltonian to get the optimal ground states for this problem. Okay? Do you have questions until here?
Sure.
Yes.
So how difficult is it then to prove that these solutions converge to an optimizer for your original problem?
Which solution?
I mean you somehow hope that if epsilon goes to
Right.
zero, these gamma epsilon sort of give you a solution, right? How hard is it to prove that?
Finite dimensional qualitative convergence, not hard. Okay, so absolutely true, especially if you don't care about too much about the speed and stuff like this. I think you can do much more.
If it takes B star limit, will it still work?
But in this case, finite dimension, there's really no difference, right?
In
Finite dimension. Yeah, right. I think qualitatively still should be okay. I mean, the problem itself in infinite dimension, one has to pay an epsilon prime more attention, right? But I think concerning the qualitative convergence in the infinite dimensional setting, once you fix the right definitions properly, I think it's doable, qualitatively.
You should get it.
Yes, absolutely. Absolutely, yeah, absolutely. I think you can do way more in the sense that, no, I'm also commenting on this in the sense that in the classical setting, what you can do is understanding even the expansion in epsilon. You can really understand how fast the energy is converging, and you see very interesting terms appearing. And this question, non-commutative, is more interesting because it's less obvious how to do it. Yes, thank you. All right, so this more or less is going to be mostly also the things that Natalia is going to talk about. I don't want to talk more about this because I want to make a few computations with you, which are simple, and I never find the time to do them. So I want to essentially modify a little bit this setting and see what happens when you try to impose fermionic constraints. Okay, so what do I mean with fermionic constraints? Well, fermionic constraints, I mean, I don't want to work with this type of product, but I want to work with the anti-symmetric tensor product. Okay, so the modification I want to do is this. I want to put here anti-symmetric tensor product, which is reducing essentially the dimension of my space. For those who have never heard of it, well, if before the tensor product was the one generated by the free tensor product, now the anti-symmetric one is the one generated by the anti-symmetric tensor product, where the basic operation you want to do is that if I take two vector and I do this operation, I want to symmetrize my product. Okay, so I want to do V tensor W minus W tensor V, and then I want to divide by 2. Yeah, so algebraically, yes? Screwed, yeah, you mean? Yes. Okay, so I just simply want essentially to encode a sort of exclusion principle, right? Because if I put V tensor V, I will get 0. And this is the algebraic way to encode an exclusion principle that physically you observe when you work with fermions. Okay, so the question is now, I mean, don't read the blackboard in the way I wrote it here. So the dimension now, of course, is not going to be this one. And to do this, I want to reduce my setting to the case where all the Hilbert spaces are the same. So I'm going to do the following thing. So I'm going to work with a different space. So I'm going to put myself in the following setting. So I want to put myself in a setting where all the Hilbert spaces are the same. So particles are indistinguishable. And now, of course, my Hilbert space, which I said is this one, they're all the same, now has dimension which is d over n, because in some sense you need to exclude the repetition, because the repetition kill your product, which means in particular that whatever I'm saying here makes sense essentially only when d is bigger than n. Physically, it makes total sense when you work in infinite dimensional setting, this condition is not there, but because we are kind of slowly working towards the infinite dimensional setting, you need to keep in mind that I'm working with a dimension which is higher than the number of the particles. Okay? Okay, so that's one thing I wanted to say. And without saying too many details, the type of Hamiltonian we want to use in this case is to have similar properties than the particles. In particular, the Hamiltonian should be something that says, talk about interaction of the particles, and because the particles are indistinguishable, we should see this also at the level of the Hamiltonian. And this means that you assume typically that the Hamiltonian has the following properties. If you swap the particles, concerning to the talk that we've seen the first day this morning, so if I conjugate my Hamiltonian with I, where sigma I is simply the swap between the ith and the last one. So if I do, for example, V1, and then I do Vn, I'm taking the ith, and I'm putting at the end. Yeah, so I'm going to skip the ith, and I'm going to put it at the end. Yeah, so you see there is a swap here from the ith to the end, and I want my Hamiltonian to be invariant by swapping. Okay, today we've seen the swap of two particles. Now we're having n particles, so we have all the different types of swapping we can do. And now you want to do exactly the same problem, so I want to minimize. Yes?
Swap, or you put,
No, I'm really taking any free tensor product here, V1, V2, Vi, and I'm going to take the ith, and I'm going to put it at the very end.
Okay, and then n does not go.
No, well, no, sorry, yes, okay, yes, right. So you just put the ith, you put it at the end. Yes. When you have two particles, it's really a swap, because you're just going to do this, okay? Right, it's more like a shifting. Yes. Okay, and then what I want to do exactly the same problem. I want to minimize my problem. Let's say, let's work it with the trace of, let's say, gamma log gamma for simplicity. But now my gamma is going to be a state, right? So an operator with the right marginals, but I only want to look at them as fermionic states. Yes, I want to pick gamma to be a state over H. Let me actually change the name. I'm going to use the minus here so that we remember that we change the space here, right? So I'm going to use a state over the fermionic space, which in other words essentially means I'm using an operator as before, but my operator now has the symmetries that we expect from a fermions. For example, if I'm looking at this physically, if I change two particles, my operator will change sign. Okay? And of course, I'm going to put the same marginal constraint. Okay, so gamma has the right marginal. Of course, because now I'm working on this symmetric space, the particles are all looking the same. So if I take the first marginal or the second marginal or the third marginal, they're not going to see any difference. So my marginals are also all the same. Yeah, so gamma I is just some gamma 1, which is a state on the first Hilbert space, for example. Okay? Yes?
I just need to comment probably, or you were probably wanted to mention it. So here you are saying that the gamma is actually now operator on an H, so the condition on the marginal is slightly different from the one that we introduced before, because before we assumed that gamma is an operator on the tensor product, so we can take the partial traces easily. So here, we can say it in the same way, if you just embed this gamma into the.
Right. So when I say I didn't change the definition of the marginal constraints, I'm saying my gamma now is a fermionic state, which means essentially that doesn't have some of the part in the decomposition of the space. The marginal constraint for me means exactly what I wrote at the beginning. So if I see this as an operator on the full space, if I test it against this identity U, blah, blah, I get exactly the right marginals. Okay, so thank you very much. I'm assuming somehow in my mind that, of course, every operator of this form is embedded in the bigger space. It just has additional constraints, and the marginal constraint doesn't change. Thank you very much.
But now there's only one marginal, right?
Who is asking? Andre.
Well, there's only one marginal.
Yes, they're all the same. Absolutely. So one thing to check. Yes.
But does gamma not have to satisfy the same assumptions as the Hamiltonian?
Sorry?
Does gamma satisfy the same assumption as the Hamiltonian?
It's not exactly the same. In this case, I'm really saying, here I just want to say that the Hamiltonian essentially is independent on the swap of the particles. This is really fermionic. This really means that if you think about this physically, if it's a pure state over a wave function, for example, in L2, then it really means that if I take xi and xj and I swap it, my function changes sign. Okay, so it's more. Yeah, it's really more. It's not exactly the same assumption. Yeah. Okay, so what I wanted to say, I think I have maybe just 10 minutes, is what happens in this setting. Okay, this kind of assumption to work with the symmetry is very natural because typically, physically, you work in this setting. Now the question is, what happens mathematically? We try to simplify our life all the time when we work with toy models, but if I actually want to implement this, what happens? And what happens in this case is something non-surprising, that if I look at the dual formula, will look similar, but something important should appear. So if I look at the dual formula now here, I'm going to see something similar. I'm going to see the sup. Now I'm going to use only one bounded operator because my particle are undistinguishable. So referring to your question, in this case, even more extreme, I'm actually having just one potential because everything is really commuting. And I'm just going to maximize u times gamma 1, just one marginal. And then here I'm going to have the same thing, so the exponential of the sum of u minus h divided by epsilon. So very similar, but now here I'm going to write a minus here, where with the minus, I'm referring to the following thing. I'm taking this operator. I'm defining the exponential as an operator on the full space. Whatever I get is not necessarily fermionic, so it's not necessarily an element here, so it's not satisfying this nice swapping relation. I'm going to take it, and I'm going to project it down to the fermionic space. Okay, so this is really a projection from, let's say, from S of H to S of H minus. Okay, so yes?
Yeah, so one of properties of fermions is that they cannot be in the same state.
Exactly.
So that is not in the swap operator, but it is in the projection.
Precisely. So actually, that's exactly the point. That's what I wanted to arrive, because I think it's interesting to see. So this problem, the comment you just made, this problem is not well posed in general as it is the other one. And the reason is this Pauli exclusion principle. So for those coming from physics, it is very well known that two fermions cannot occupy the same state at the same time. Mathematically, you see it as a constraint on the type of marginal that you can get. If I have a fermionic operator and I compute the marginal, I'm going to get something which has necessarily some constraints on the spectrum. Yeah, when you say there is no more than one particles inside your state, it means that the maximal eigenvalue of your one-body reduced density matrix is at most 1. In this case, because I'm coming from optimal transport, I'm renormalizing everything to 1. So in this case, Pauli's principle, instead of being 1, which is physically more appealing, is going to be 1 divided by n. But the only reason is that I'm renormalizing everything to 1. Okay, so every eigenvalue of gamma, so let's say my gamma, my marginal, my gamma 1 has to be smaller than 1 divided by n, the identity. And with this notation, it means that every eigenvalue is at most 1 divided by n. Okay, so if I write gamma in the spectral decomposition, I look at the eigenvalue, I cannot get something above 1 divided by n. Meaning that there is really no matrix here, doesn't exist any matrix here that gives me a marginal which has an eigenvalue which is bigger than 1 divided by n. You can try, you will never get it. And I want to conclude this talk. I hope I could do the computation, I don't have the time, but I want to conclude with the following observation here, somehow this theorem. So if you look at the primal formulation is not well posed if I don't assume Pauli, right? But this functional here is really, I can write this formula regardless of the assumption that I have on gamma. So I don't need any type of assumption on the maximal spectrum of gamma 1 here to write this right-hand side. So this formula makes total sense also when I don't have the constraints. Of course, if I'm claiming that there is a duality here, I should better be able to prove that if I don't satisfy Pauli, then this sup should be plus infinity. Yeah, because the left-hand side is actually not defined. So I should be able to see this. And it's actually very interesting. You can really see it by hand, even if you don't come from physics, you come from a variational perspective, you can really see that Pauli is satisfied. So let's say gamma 1 is smaller than 1 divided by n, the identity, if and only if the sup of the dual problem, let's say I would call this functional here, the, how did I call it before? Minus, so sup over u of d epsilon minus of u is finite. So the sup is finite if and only if I have Pauli. And maybe more interesting, which I personally don't understand from a physical perspective, if I ask myself, well, when I actually do have a maximizer, and the answer is that then I have to satisfy what we would call a strict Pauli constraint. Okay, so actually gamma 1 has to be between 0 and strictly smaller than 1 divided by n. And this is going to be if and only if there exists a maximizer. Okay, so if I actually want to have the maximizer, I really better not have exactly saturating constraints at the level of Pauli. Yes?
It makes sense because you have a temperature.
Okay.
It's very, I mean, I would have expected it.
Yes, and I'm actually curious. I wanted to ask, that's also why I'm talking about here, to ask a bit more the more physical interpretation on that, yes. And from a more variational perspective, the interesting thing is that you can really construct the potential in a very explicit way. Okay? So I don't have the time to do this, so I'm going to probably stop here. But how do you actually see that these Pauli constraints appears at the level of the dual functional? What you have to do, you have to consider, I'm just going to write it down here. So you write your gamma in the composition, so you write it as, let's say, lambda I, vi. And then you're going to define for n, I'm going to define a potential, which I called un, which is actually commuting with the marginal. So I'm going to have uin vi. And I do it very explicitly. So I'm going to put, let's say that lambda 1 is the biggest eigenvalue. I'm going to do n on the first eigenvalue, on the first eigenspace, and on all the other, I'm going to do minus n divided by n minus 1. Okay, so on all the others. So I'm going to, from a potential perspective, from the dual perspective, if you want to see why the dual functional is sensitive to the property of Pauli, you're going to create a potential which is putting a lot of weight on the eigenspace where possibly Pauli is not satisfied and very negative on the other one. If you compute the dual property, you see Pauli appearing in a very natural way, even if he had no idea that this was actually coming from a physical perspective. Okay? So you can really do the computation explicitly. I think that I'm not going to do it. And in the case where Pauli is at the border somehow, so in this case, so when gamma is exactly 1 divided by n, what is going to happen is that this potential, which has a norm which is going to plus infinity, actually have bounded energy. Okay, so you're losing coercivity when you are at the boundary of this constraint. That's why you're not going to have a maximizer. Okay? All right, I will stop here. Thank you very much.